the next question that arises whether there are any functions at all for which the limit doesn't exist. So this is about the non-existence of limits. Well, there's a very practical example where you can see that this is indeed the case. And this example concerns our Mother Earth. I will make a picture of her. First in pencil, and I will make it visible to you now. Suppose I'm at the equator, say at 0 degrees longitude, and I put some friends along the equator, 23 friends, so one is at minus 15 degrees longitude, so his time is 1 hour earlier than my time. I put the next one on minus 30 degrees longitude, so his time is 2 hours earlier, and so I continue along the whole equator, and the 23rd has a time, the time of the 23rd is 23 hours earlier than my time. Now what we do, we've played the following game. We all walk upwards our own meridian to the North Pole. North Pole is here, and we move upwards at the same speed. So this means that all time, my first friend here is the time, he has a time which is 1 hour earlier than mine, the second has a time that is 2 hours earlier than mine, and so on. So this keeps on till we come, and even though we come closer and closer to the North Pole. So let us zoom in on this event. So we are maybe at 1 centimeter difference from the North Pole, and still I'm walking upwards. My first friend has a time which is 1 hour earlier than my time. The second is 2 hours earlier. And this remains the case, even though we shrink this even more, till we are at 1 millimeter distance from the North Pole. We still have the same time differences. If you think of this, then this implies that if you call our position x, and you let our position become closer and closer to the North Pole, then the time at the position x, the limit of the time at position x, and we get closer and closer to the North Pole, doesn't exist. My time will always be the time of my first friend will be always 1 hour earlier than my time. The time of my second friend will always be 2 hours earlier than my time, and so on. And the funny thing is that there is no way to define time at the North Pole such that we are all happy. Suppose, for example, that the time at the North Pole would be my time when I arrive at it as a limit. Then what would happen to my friends? Well, my first friend would when he would put his foot on the North Pole, he would make a time jump of 1 hour. The second, when he puts his foot on the North Pole, that would be possible to put all our foot together on the North Pole, would be a jump of 2 hours, and so on. So this is a very natural function where limits do not exist at all. We will not really address how to calculate limits, but I want to make some small remarks, and I'll tell you something about one type of exercise we will be doing. So most functions that we will consider, then limits tend to exist, and what you can do is just plug in the limiting value. That's equals a into our function. Problems may occur, and you will see these functions. And these problems may occur in two particular cases: when functions make a jump at a. We will discuss this case a little bit later. And the second one is when the function we consider, which are fractions, and a special sort of fraction, namely when the case when plugging in the value x is a into our function, then we get the result 0 divided by 0. Okay. We will give some examples of the latter. So, suppose that we have the function x squared minus 4 over x, and we want to calculate the limit for x approaching 2. Well, this function is nothing special with this function, and if we plug in the limiting value, we get 2 squared minus 4 equals 0, divided by 2 is 0. Nothing special, so this limit exists. Now we make it a little bit more complicated, and we look at the function x squared minus 4 divided by x minus 2. Now this is of course again a fraction. Plugging in the value at 2 gives us 0 for the numerator and 0 for the denominator. So we plugging in the value 2 gives us 0 divided by 0. So we have to think in this case what will happen. Now thinking makes us look at the form of these functions, and the numerator is in fact a polynomial of degree 2, and we know that we can factorize it since it has two zeros, namely x equals 2 and x equals minus 2. So we can write it as a product of x minus 2 multiplied by x plus 2. The denominator is still x minus 2, and you know from theory of fractions that we can cancel out common factors in numerator and denominator, and so we get that we have to calculate the limit for the function x plus 2. And if we plug in the value at 2, we get 2 plus 2 equals 4. One more example which is similar in complexity, but instead of putting x squared minus 4 into the numerator, we put 1 over x minus 1 over 2. Okay, we have to subtract fractions in the numerator, and then it's always convenient to do so we have to make them the denominators equal, and this means that we have to make the denominators, or we can make the denominators equal to 2x, and to do so we have to multiply the numerator of the first by 2 and the second, and the numerator of the second by x. So we get the following thing: 1 over x becomes 2 over 2x, so we multiply numerator and denominator by the same factor 2, and the second we get x over 2x, because we multiply numerator and denominator of 1/2 by the same factor x. Okay, we divide by our original x minus 2. Of course, to divide by a fraction is, you can see this as a fraction, x minus 2 over 1, is to multiply by the reversed fraction. So, and the reversed fraction is 1 over x minus 2. For the numerator, we can now subtract both fractions, which gives us 2 minus x over 2x, and we get this result. Okay, now you see that the numerator, this numerator, and the denominator over here differ a term minus 1. So we rewrite a little. 2 minus x is minus x minus 2. And now we see that we have a numerator x minus 2 and a denominator x minus 2 over there. And we can cancel out common factors. And so we get the limit. We have to calculate the limit for x tending to 2 of the function minus 1 over 2x. And plugging in the limiting value gives us minus 1 over 2 times 2 is minus 1/4.